New generation switching power manager with USB on the go. Linear technology. Welcome to this training module on linear technology. USB technology has increased the convenience of electronic devices. Now it is possible to charge a device from the same USB port that performs the data transfer, eliminating the need for a separate wall adapter. However, there are power limitations, 2.5 watts maximum, when the USB is used for charging a device's battery. A USB-based battery charger must extract as much power from the USB as efficiently as possible to meet the stringent space and thermal constraints of today's power-intensive applications. Managing power flow within the product is another issue. Larger batteries require either higher charging current or additional time to charge to their full capacity. This need for high-efficiency charging, combined with the high level of feature integration required of the battery charger IC, need to save board space and increase product reliability. The new generation of power management ICs, such as the LTC3576 from Linear Technology, are equipped with features such as PowerPath Control, as well as other advanced integration functional blocks, such as the USB on-the-go boost converter and efficient programmable switching regulators to simply and easily solve the design challenges mentioned above. In fact, in many systems on one PMIC is sufficient to power the entire system, which is achieved through utilization of selective integration level to offer a compact solution without any performance compromises. A key feature of the LTC3567 is PowerPath Control. This automatic load prioritization offers the ability to autonomously and seamlessly manage power flow between multiple input sources such as USB ports, wall adapters, and the battery, all while preferentially providing power to the system load. In a traditional battery-fed charging system, the user must wait until there is sufficient battery charge and voltage level available to obtain system power. Conversely, PowerPath Control allows the end products to operate immediately when plugged in, regardless of the battery's state of charge, commonly referred to as instant-on operation. The power delivered from V-bus to V-out is controlled by a 2.25 MHz constant frequency bidirectional switching regulator operated in step-down mode. To meet the maximum USB load specification, the switching regulator contains a measurement and control system that ensures that the average input current remains below the level programmed at CL/PROG. For USB on-the-go applications, the double-duty bidirectional PowerPath switching regulator acts as a step-up converter to deliver power from V-out to the V-bus to both run the application and charge the battery. The power from V-out can come from the battery or the output of the external high-voltage switching regulator. As a step-up converter, the bidirectional switching regulator provides 5 volts on the V-bus and is capable of delivering a minimum of 500 milliamps. USB on the go can be enabled by either the external control pin, EN/OTG, or via an I2C interface. The input current limit is programmed by the ILI-M0 and ILI-M1 pins or by the I2C serial port. The input current limit has 4 possible settings ranging from the USB suspend limit of 500 microamps up to 1 amp for wall adapter applications. The table shows the current limit settings of using ILM0 and ILM1. When the switching regulator is activated, the average input current will be limited by the CL/PROG programming resistor according to the expression as shown. The IVB US0 is the quiescent current of the LTC3576. The VCLPROG is the CLPROG servo voltage in current limit. RCLPROG is the value of the programming resistor, and HCLPROG is the ratio of the measured current at VBus to the sample current delivered to CLPROG. You can refer to the electrical characteristics table for values of HCLPROG, VCLPROG, and IVBUSO. The wall, ACPR, and VC pins can be used in conjunction with an external high-voltage step-down switching regulator such as the LT3480 or the LT3653 to minimize heat production when operating from higher voltage sources. BAT track control circuitry regulates the external switching regulator's output voltage to the larger of VBAT plus 300 millivolts or 3.6 volts. This maximizes battery charger efficiency while still allowing instant-on operation when the battery is deeply discharged. When high voltage is applied to the external regulator, WALL will rise toward this programmed output voltage. When WALL exceeds approximately 4.3 volts, ACPR is brought low and the BAT track control of the LTC3576 overrides the local VC control of the external high voltage step-down switching regulator. Therefore, once the BAT track control is enabled, the output voltage is set independent of the switching regulator feedback network. The LTC3576 each have an internal ideal diode as well as a controller for an optional external ideal diode. Both the internal and external ideal diodes are always on and will respond quickly whenever Vout drops below BAT. If the load current increases beyond the power allowed from the switching regulator, additional power will be pulled from the battery via the ideal diode. If power to the V-bus, USB or wall adapter is removed, then all of the application power will be removed by the battery via the ideal diodes. If the LTC3576 are configured for USB suspend mode, the bidirectional switching regulator is disabled and the Suspend LDO provides power to the Vout pin. This LDO will prevent the battery from running down when the portable product has access to a suspended USB port. Regulating at 4.6 volts, this LDO only becomes active when the switching converter is disabled. To remain compliant with the USB specification, the input to the LDO is current limited so that it will not exceed the low power or high power suspend specification. If the load on Vout exceeds the suspend current limit, the additional current will come from the battery via the ideal diode. The low quiescent current, always-on LDO regulator is used to provide power to a system push-button controller, standby microcontroller, or real-time clock. The LDO is powered from Vout and therefore will enter dropout at loads less than 20 milliamp as Vout falls near 3.3 volts. When a battery charger cycle begins, the battery charger first determines if the battery is deeply discharged. If the battery voltage is below VTRKL, typically 2.85 volts, an automatic trickle charge feature sets the battery charge current to 10% of the program value. If the low voltage persists for more than half hour, the battery charger automatically terminates. Once the battery voltage is above 2.85 volts, the charger begins charging in a full power constant current mode. The battery charger has a built-in safety timer. Once the battery charger detects that the battery has reached the float voltage, the 4-hour safety timer is started. After the safety timer expires, charging of the battery will discontinue and no more current will be delivered. The LTC3576 may receive commands from a master device using the 2-wire I2C interface. A bus master signals the beginning of a communication to the slave device by transmitting a start condition. A start condition is generated by transitioning SDA from high to low while SCL is high. When the master has finished communicating with the slave, it issues a stop condition by transitioning SDA from low to high while SCL is high. The bus is then free for communication with another I2C device. The I2C serial port can be disabled by grounding the DVCC pin. In this mode, the LTC3576/LTC3576-1 are controlled through the individual logic pins Enable 1, Enable 2, Enable 3, Enable on the go, IL, IM0, IL, IM1, SDA, and SCL. The LTC3576 and LTC3576-1 contain 3 general-purpose 2.25 MHz step-down constant frequency current mode switching regulators. 2 regulators provide up to 400 milliamps, and a third switching regulator can provide up to 1 amp. All 3 switching regulators can be programmed for a minimum startup voltage around 0.8 volts and can be used to power a microcontroller core, microcontroller I/O, memory, disk drive, or other logic circuitry. All 3 switching regulators have I2C programmable set points for on-the-fly power. When 2 on-the-go devices are connected, one will be the A device and the other will be the B device, depending on whether the device is connected to a micro A or micro B plug. The A device provides power to the B device and starts as the host. Figure 1 shows an on-the-go device using the LTC3576 acting as the A device. Additional capacitance can be placed on the V-bus pin of the LTC3576 when using the overvoltage protection circuit. When an on-the-go device using the LTC3576 becomes the B device, as shown in Figure 1, it must send out a data line pulse followed by a V-bus pulse to request a session from the A device. The on-the-go device designer can choose how much capacitance will be placed on the V-bus pin of the LTC3576, and then generate a V-bus pulse that can distinguish between a powered down on-the-go A device and a powered down standard. Here is an application example for USB Power Manager with low battery startup and USB on the go. Here shows the application for a high-efficiency USB automotive power manager with overvoltage protection, reverse voltage protection, low battery startup, and USB on the go. The circuits to interface with a microcontroller, input current limit setting, and logic and I2C are same as the application 1. Please refer to the last page. Here shows the application for a high-efficiency USB wall power manager with dual overvoltage protection, reverse voltage protection, low voltage startup, and USB on the go. The circuits to interface with a microcontroller, input current limit setting, and logic and I2C are the same as application 1. Please refer to the last page.